All right, so today we want to look at the common ion effect. So in order to do that, we do have to review the solubility of salts a little bit. That's not what I want. I need to turn on my visualizer. All right, so there we go. So if you recall, grab this other periodic table real quick. You have these solubility rules. The key ones that they will use for you are usually they'll give you alkali metal. Anything with an alkali metal is definitely very soluble, and ammonium or anything with a nitrate anion. So ammonium, NH4, it's the one positive polyatomic ion we use quite a bit, except for hydronium when we get to acids. And then nitrate, the negative ion. Anything mixed with these are soluble. And then there's kind of these ones that always kind of stick out. The halogens, except for fluorine, mixed with silver, lead, mercury, or copper. And things like calcium hydroxide, right? Most of the time, again, if you look, it's soluble with those alkali metals and then ammonium, but anything else insoluble. I mean, when you look over these, that's kind of the trending thing. So if you remember these top three things, you're going to be able to do most of this. There's just these, like the, again, like I said, the halogens and stuff like that that kind of sneak in. That's the activity series. The other big thing about this is we need to make sure we remember the net ionic equation. So if we're doing the net ionic equations, for this one, this is the formation of the precipitate. A lot of times what we'll see is the solvation of the solid substance. So we break it down. Remember, K sub EQ with this has a specific name called the solubility product constant. So change it to KSP. If they give you the concentration, then you can find the KSP. If they give you the KSP, then you basically have to put in those X's and solve for that. And since this is a 1-to-1 combination and a 1-to-1 ratio, each of these would just be X, which is that concentration right there. So it just pumps in. The KSPs are all over the internet and your book. Keep in mind that they do change with temperature. This makes sense for us because if we take salt or something like sodium chloride, we can dissolve a higher amount of salt in warmer water. That means that the KSP at a higher temperature for sodium chloride would be higher. That becomes a factor. Like, for example, those that came in today, the sidewalk and the roads are kind of icy. You know, we use salt to put on the roads to kind of take care of that, to get in there and basically dissolve. And one of the things that happens is that you could be dealing with a solubility problem if the temperature got down too low. That's why they say that even at low extreme temperatures, salt will not work as effectively. And that's because then you're dealing with a solubility issue. Here's another breakdown of a problem. This is lead 2 chloride, and it's breaking down into lead and 2 chlorines. They gave you the concentration of the lead ion. So that means that they gave you this. If they gave you the concentration of the chloride ion, then that is 2x, right? So you would have to divide that by 2 to get the lead ion. And since every 1 mole of this makes 1 mole of lead and 2 moles of chloride, to find the actual molar solubility of the solid, if they gave you the chloride ion, you'd have to divide it by 2. Just keep in mind when you're looking at this, 1 mole of this makes so many moles of this, makes so many moles of that. You've got to kind of keep that straight in your head. If you're watching the videos, I think it's the woman that we didn't watch it, we just saw a picture of her. But if you're watching the videos on the KSP, you might see somebody use S instead of X. I just wanted to make sure that you understood that that is the same thing. They're just saying, I guess solubility concentration or something like that. They're regarding it using S to solubility or something. I'm not sure why. Maybe they're tired of seeing X's everywhere. The two most common mistakes is to forget to put that exponent on the term. So whenever you have that 2x here, you also need to, when you put that on the top of the KSP, you need to make sure that you square it. I find myself making that same mistake. So just keep that in mind. It's one of those things like if your mind's not into it and it's wondering, you might forget that. And then forgetting to do the stoichiometry to get the correct values. So after they find x, they forget to go back and say, oh right, we have to have 2x of that. Cool. Questions on that? That's a quick review of the KSP. All right, then let's do the CommonIon Effect. Who do we usually have in here besides you guys? Wasn't there somebody else yesterday? She's not. Nope, she's on it. All right. So far we've considered ion solids in pure dissolved water. What happens if the water contains an ion in common with the dissolving salt? So if we have AB yielding a plus B, right? And we were to use our ice table, and we already have some B. The Chatelier's principle says what? If we already have some of this, then that means that we may be shifting back that way, right? If there's enough, or, and we'd have to look at the case of SP for that, but, or whatever amount of this that we can make into this, we're not going to be able to make as much because of that KSP ratio. There has to be so much product, and in this case, to one solid. So keep in mind, what if the water contains an ion in common? We probably won't have as much solubility. So just to make sure we're all back on the same page, let's do the KSP of AgCl is 1.8 times 10 to the negative 10th. If they don't give you a temperature, we just assume it's at like, 25 degree, like standard temperature. Not the gas standard temperature, but standard temperature. So calculate the solubility of AgCl. So we need that equation, the breakdown. We're going to first do it in water, and then we're going to do it in 1 molar sodium chloride. So we have KSP equals, and here we have our R, initial change, equilibrium. And again, these are great for helping you set them up, but they do take a little bit of time. We don't care what's there, or there, because it's just one for us. So here we have none of this to start with, none of this to start with, plus x, and then x and x. So the initial was 0. As time went on, we added x. At equilibrium, we're going to have x and x. So the KSP again is the AG, CL, and what's going on the bottom of this? Just one, good, right? So now all we're going to do is put X and X there. So 1.8 times 10 to the negative 10th equals X times X, which is the same as X squared, right? So we'll take the square root. And I noticed on these calculators, and I don't know if you guys have the same version as me, but I noticed on these guys that they, the cubed root and stuff like that is hard to find on these. I thought that kind of stunk. You have to go under math, but square root of 1.8 times 10 to the negative 10. I got 1.34 times 10 to the negative 5th. And that would be the concentration of Ag and Cl negative, which actually is the molar solubility of the AgCl there. Because if we were to take a look, we should be able to dissolve 1.34 times 10 to the negative 5th moles for every liter of AgCl. That would give us that many moles of that ion and that many moles of that ion. Right? All right. So in 0.1 moles per liter sodium chloride. So why is Cl negative the common ion? Because both silver chloride and sodium chloride have that Cl. So again, here, our ICE table. I'm going to ignore the AgCl here. We have initially 0 Ag, but we have 0.1 moles per liter of the Cl. The change here, again, since we have 0 Ag, what does the system have to do? The Chatlayer's principle? Yeah, it has to make some Ag. So it's going to favor the forward reaction, right? It's going to favor the forward reaction. If we wanted to, we could compare it to this, right? This is a pretty small number, but it's going to make some of this. We can't just have 0 Ag. Then the change here is going to be plus X and plus X. And then this is going to be X, and this is going to be 0.1 plus X. Yeah. All right. So then we have the same KSP above. We're going to have 1.8 times 10 to the negative 10th equals X. And here we can ignore this X because it's going to be so small, it's not going to get near the significant digits of 0.1. So now, of course, instead of ignoring, you can always use the solver function or the quadratic equation. So that's going to be X times 0.1. So what do? We take 1.8 and we basically divide it by 0.1, which becomes 1.8 times 10 to the negative 9th moles per liter. And that is equal to the concentration of the Ag. And the concentration of the Cl negative, anybody want to tell us what it is? What is that? Starting these classes with that song, I'm alive and awake and whatever it is. You know that song? You think that you're alive and awake and ready to take on the day. Anybody? What is 0.1 plus this? No.
Just 0.1.
Yeah. 0.1. One thing you can do is let's see, 1.8 times 10 to the negative 9. You can check to see like what percentage of this, and if it's, this is called the 5% rule. And basically, if this is not within 5% of this, obviously it's not going to if this is less than 5% of this, then this is not going to affect it at all. That's a common way to call it. I think there's another name that they use for it. 100 times rule. Same thing, like we are so far away from this, 100 times this isn't even close to this. So there's nothing that this can do to affect this number. I know that this only has one significant digit, but even if we had another whatever, 8 significant, it's not going to matter that much. So if we take a look, what would be different about this problem? PbCl2, what's that going to break down into? There we go.
Pb2 plus
and 2Cl negative, right? Pb2 plus and 2Cl negative. The key here is some students get confused and say, well, isn't Cl diatomic? Well, we're not talking about elemental Cl here. We're talking about water molecules surrounding that Cl negative and basically pulling those apart separately. So don't get confused on that. So if we take a look, again, we have a 0.1 molar CaCl here. So that's going to be our common ion is Cl2. And basically it's just looking for the ion that's the same between each two. So we are going to have initially 0.10 moles per liter of the CaCl, of the Cl2, of the 2Cl. We're going to add 2x. We're going to get 0.1 plus 2x. Here we're going to have 0. We're going to have x at the end at equilibrium. Again, just following suit. So now we have 1.7 times 10 to the negative 5th. Key thing here being that we have, and I'll go ahead and rewrite it so that you can look at this later if you need help. But this Cl negative is going to be squared, right? So now I want to put these changes in there. I'm sorry, I want to put these concentrations at equilibrium in there. 1.7 times 10 to the negative 5th equals x, and then 0.10 plus 2x squared. Right? Now, we can ignore the addition thing. So we can ignore the plus 2x here. So that can become, what is 0.1 squared? It's just 0.1. You guys are better at this than me, right? 0.01. So we have 0.01 x here. And that is equal to 1.7 times 10 to the negative 5th. So take that 1.7 times 10 to the negative 5th. And we will divide it by 0.01. The only thing we're ignoring is that 2x. Because it's so small compared to 0.1. Let me show you real quick. So we end up getting x equaling 0.0017 for that. So if we add 1.0 let me do it down here. If we add 1.0 plus, and this will be times 2 because it's 2x, right? 0.0034. What is the real answer? Remember, addition subtraction deals with least number of significant digit places, right? Least specific. So we would end up getting 1.0034, but when we do our rounding, we're to the 10th place. So what happens to this? Yeah, it just would drop. That's why we can ignore that that there. And again, you can put this through the solver function in your calculator, and you're still going to end up getting the same. These amounts are just so small that they don't have an effect on that. So if x equals 0.0017, the concentration for the CL is still going to be 0.1, and the concentration for the PB plus 2 will be 0.0017. The molar solubility for the PbCl2 in a 0.1 molar calcium chloride solution would be that 0.0017. You can try 3 on your own. Here are some more practice problems dealing with the reaction instead of the KSP. Now here's kind of one of those how to take this to a different level. So we get that we've been solving things for moles per liter, but you can change from moles per liter to grams per liter. So let's go ahead and do this. The KSP for CaCO3, calcium carbonate. That breaks down into calcium 2 plus and carbonate 2 minus. Is my pace okay? My pace okay? Yeah, okay. So if we take a look here, initial, well, again, we're pretty good off here. We don't have any issues. We're at standard temperature, and here is the KSP. We don't have any pre-existing things, so both of these are 0. So the change will be plus x and plus x. That makes it x and x. So that means that we will get x squared equals 3.8 times 10 to the negative 9. Right? 3.8 times 10 to the negative 9. Oh, I always forget these calculators. You gotta hit that first. Oh. Can I just do that? Nope. What the heck is that weird thing there? Oh, it wants me to rewrite it. We get 6.16 times 10 to the negative 5th. That's the concentration for both Ca 2 plus and CO3 2 negative. That is also the molar solubility because it's a 1 to 1 to 1. So that means that if I take a look, I can dissolve 6.16 times 10 to the negative 5th moles per liter of CaCO3, right? So what if I was wanting to, and I'm just going to change this a little bit to make it more interesting for us. What if I only had 50 milliliters? How many grams of CaCO3 could I dissolve in that? So all we're doing here is using our old stoichiometry, our old dimensional analysis again. So every 1,000 milliliters is 1 liter. every 1 liter of this stuff. From that, remember, all of these are the same. They're all 6.16 times 10 to the negative fifth moles per liter. So every 1 liter of this will do 6.16 times 10 to the negative fifth moles. And every 1 mole of this is 40.08 plus 12.01 plus 16 times 3. So every one of those is 100.09. So we take 100.09 times 6.15, I'm sorry, 6.16 times 10 to the negative fifth, divided by 1,000 times 50. So we get 3.08 times 10 to the negative fourth grams of this calcium carbonate to dissolve in. Now, if we were to just answer their question, we would have taken this 6.16 and times it by 10 to the negative fifth, then multiplied that by 100.09. That would be 0.00616. That would be the grams that you could have per liter, right? So then we didn't have a liter, we only had 50 milliliters. And there we go. Either way works. This is the way that sets it up in my mind, the easiest. Questions there? No. All right then, last thing for today. I'm going to get you started on this, and then I'm going to let you finish. So if you take a look here, you should be able to do A on your own. And I'm going to help you with B. How many grams of silver bromide can be dissolved in 50 milliliters of a 10 molar ammonium solution? So we have a little issue here. We've got these two. Here's the KSP, and then here's the K formation. But these Ks, if you recall, we can use Hess's law to rearrange these as needed. As long as we do whatever we do to the reaction, we do to the K. So if we reverse the reaction, what do we do to the K? To the negative. If this is K now, right? These aren't the delta H's. Yeah. So if we reverse the K, remember it's products over reactants. Right? That's what K is, products over reactants. And I'm just doing this kind of general right now. But if we reverse the reaction, what do we do to the K?
You have to like put 1 over it.
Yeah.
Like reverse it.
We inverse it, right? If we double the reaction, if we multiply the reaction by a common coefficient, what do we need to do to the K? If I put all of these as 2, what's that going to do to all of these things? Louder? But multiply isn't the right term. If I put a 2 in front of each one of these, what am I going to do to this reaction here, this equation here? You got it. So then you would take it to that power. You would take K to that power, right? If we halved all these, we would then have to take this K to the half power. And all it is because if we put a 2 in front of there, remember it does go up here. If we put a 2 in front of each of these, then we have to square each of these, right? Yeah, yeah. All right. So I'm going to start with B. So I'm going to drop down a little bit here. That way you can solve the other one. I would suggest you do that too on your sheet. This is how many grams of silver bromide can be dissolved in 50 milliliters of a 10 molar solution. So the first thing we have to do is we have to look at these equations. All right, so looking at this, we know that this is going to be 1 because this is it solid, right? That's not going to affect any of my case. This is aqueous, so that is going to be a factor. Everything else is aqueous. But looking at this, if we get this made, then that will make more of this, which will make us go where? Make us go forward. So looking at this, if we want to figure out how many grams of silver bromide can be dissolved in 50 milliliters of a 10 molar solution of ammonia, we're already going to have some of that ammonia there, right? So if we take a look at this, we're going to be able to get rid of these because this is getting used up. That's going to get us to, we don't care about the AGBR really anymore, but we're going to want to put it in there. It's solid still, so it's not going to have a factor. AGBR plus BR negative yields the plus the 2NH3 yields the AgNH3 2. So there are our factors. This one's not going to be a big deal. So our product here is AgNH3 2. Our we're going to have NH3. Oh, sorry about this. Yeah, I just got caught in class. Thank you so much. Somebody just told me I had BR on the wrong side. Good call. Negative. BR is a product up here, right? So we need to make sure we get that product on this side, right? So that's going to put BR negative up here. And then NH3, and what am I going to have to do to it down here? Square it, because I have 2 right here. So if we take a look, this is going to be equal to our new KSP, our new K in a sense. So if here's our reaction. We've taken out these guys. So if we were to take a look at this, basically we have Ag Br negative over 1 times AgNH3 2 over NH3 squared, right? That's each of these separately, sorry, and then Ag here. What's going to happen to the Ags when we do this? They will cancel out. When we take this times this, we get this. So that means that we need to take, instead of adding like you do with delta H, right? We need to take this times this to get the new K. decay, we'll call it decay 3. Boom, boom. So how much of this this NH3 do we start with? Well, we are starting with a huge chunk of that at 10 moles per liter. How much of the AgNO3 do we have at the beginning? We've got 0. And we don't care about this one, right? And the Br, we've got 0 because again, we are adding grams of silver bromide to this solution of NH3. So what's going to happen? We are going to minus 2x plus x and plus x. Yeah, if I wouldn't have done that, then I would have done. So that means that our concentration for NH3 is 10 minus 2x. Our concentration for AgNH32 is x, and our concentration for Br negative is going to also be x. So again, I've got the Br on the top right here. So that's going to be x. We have the AgNH3 2. That's going to be x, and we're going to put this all over 10 minus 2x squared. What is this equal to? Well, we've got to multiply those Kp, the Ksp and the Kf. 3.3 times 10 is negative 13 times 1.7 times 10 is 7. We get 5.61 times 10 to the negative 6. So at this point, what can we do? Well, we've got x squared on top. What can we do with this minus 2x? What's that? One more time. You could square root everything. That would work too. But we can also ignore that. Why don't you square root and let's see how far off we are from each other. Do you have your calculator? 10 squared. That's 100. 5.61 times 10 to the negative 6. So 5.61 times 10 to the negative 6 divided by 100. I'm sorry, times 100. And then we will square root that answer. You get 0.024. So here's the key now. That means that we have 0.024 for the concentration of the Br negative. Right? And that also equals the molar solubility of the HBr, because for every 1 Br we get, we dissolve 1 mole of AgBr. This is the mole. You get 0.024, man? Cool. So that's moles per liter. Well, what do we have to do? Well, it's the same setup as before. What is AgBr? 79 plus 107.87. 79.10. 9. 187.8. So if we take a look, 0.0, actually we want to start with 50 milliliters. Every 1,000 milliliters is 1 liter, and you can always do all this stuff in your head if you want. And every 1 liter has 0.024 moles, and every 1 mole is 187.77 grams. 50 divided by 1,000 times 0.024 times 187.77. How do I look at that again? I'm trying to do that right. Yep. We get 0.22532. And that's grams. Questions there?
I still don't understand where you got that 10 from for the 10 minus 2x.
It says we have 10 molar ammonium up here. That's what we're putting it in. We're dissolving this in that 10. So at that point, whenever we are looking at the new reaction that we have, the new one that we got from Hess's law from doing this, we need to start initially with 10 of that ammonia, 10 moles of that ammonia. So it's the initial concentration of that ammonia. All right, so I suggest you do A up here, and I would try these problems. I'll post the answers to those later today. Again, you know, that's the work that is needed for that question. This was a pre-response question in 1971, and looking through it, there's been, I believe, one more question like that, and we'll put that on another review. But it doesn't seem like it's as common as some of the other themes, but you know, that's it. That's one of the things you could do. What I did see is that it's more common to give you two things like this, and then make sure that you can get them to equal out. This one is pretty easy because all you've got to do is multiply these. But let's say that in order to get this to equal out, you had to double the top. Then you would have to remember, before you multiply these together, you would have to square. If you had to multiply the top by 2, then you would have to square the KFC on that. All of that is right here. This is wow, I didn't do page number. It's on page 3. It must be hidden by this. But so when you are adding equations, you actually multiply them together because to get the new K. If you make a change, here is the changes. So if you add balanced equations dealing with K, you actually multiply the K's to get that factor up. All right. It's Friday. Again, I think what we said is that we will do I will give you Monday, Tuesday, and Thursday to do won't be a test, it'll be the completion. Help me out, what are they called? Progress check for equilibrium. I haven't had a chance to look at it yet. I've been quite busy. But if there is like a one that we haven't covered yet, we'll cover that on Wednesday. And then we'll probably move on when we get back. after that awesome 4-day weekend we're all looking forward to. Have a great day, guys. Have a great weekend. If you have questions, by all means, stick around. William, you there?
Yep.
Yep.
Thank you.
How much snow do you think they got this weekend, this week so far down there? Have you checked the weather report down there?
No, I haven't.
I was wondering if you guys were going this weekend again.
No, unfortunately not.
Yep. Take care.
Thank you, Mr. Chad. Have a good day.
You're welcome. Bye.